Hey everyone, welcome back to Engineer Empire. I'm a software engineer turned corporate VP and head of technology. I dive into topics like engineering, finance, and business. If that interests you, please hit like or subscribe. Today I'm reacting to Why Are Smokestacks So Tall?
The big black stacks of the Ilium Works of the Federal Apparatus Corporation spewed acid fumes and soot over the hundreds of men and women who were lined up before the red brick employment office. That's the first line of one of my favorite short stories written by Kurt Vonnegut in 1955. It paints a picture of a dystopian future that thankfully didn't really come to be, in part because of those stacks. In some ways, air pollution is kind of a part of life. I'd love to live in a world where the systems, materials, and processes that make my life possible didn't come with any emissions, but it's just not the case. From the time that humans discovered fire, we've been methodically calculating the benefits of warmth, comfort, and cooking against the disadvantages of carbon monoxide exposure and particulate matter less than 2.5 microns in diameter. Maybe not in that exact framework, but basically since the dawn of humanity, we've had to deal with smoke one way or another. Since we can't accomplish much without putting unwanted stuff in the air, the next best thing is to manage how and where it happens to try and minimize its impact on public health. Of course, anytime you have a balancing act between technical issues, the engineers get involved. Not so much to help decide where to draw the line, but to develop systems that can stay below it. And that's where the smokestack comes in. Its function probably seems obvious. You might have a chimney in your house that does a similar job. But I want to give you a peek behind the curtain into the Ilium Works of the Federal Apparatus Corporation of today and show you what goes into engineering one of these stacks at a large industrial facility. I'm Grady, and this is Practical Engineering. We put a lot of bad stuff in the air and in a lot of different ways. There are roughly 200 regulated hazardous air pollutants in the United States, many with names I can barely pronounce. In many cases, the industries that would release these contaminants are required to deal with them at the source. A wide range of control technologies are put in place to clean dangerous pollutants from the air before it's released into the environment. One example is coal-fired power plants. Coal, in particular, releases a plethora of pollutants when combusted, so in many countries, modern plants are required to install control systems. Catalytic reactors remove nitrous oxides, electrostatic precipitators collect particulates, scrubbers use lime, the mineral, not the fruit, to strip away sulfur dioxide. And I could go on. In some cases, emission control systems can represent a significant proportion.
While he's referencing smokestacks here, a lot of what he's highlighting, like even these, are technically steam and vapor. They're not actually pollutants in all of the images that he has in the background. Hopefully nobody is immediately alarmed by all of this pollution that is just like constantly billowing out. In many cases, these are steam that he's referencing. I think they're just much more visually striking, as you can see in this photo, for instance, or this video that's playing behind right now.
Of the costs involved in building and operating a plant. But these primary emission controls aren't always feasible for every pollutant, at least not for 100% removal. There's a really old saying that the solution to pollution is dilution. It's not really true on a global scale. Case in point, there's no way to dilute the concentration of carbon dioxide in the atmosphere, or rather, it's already as dilute as it's gonna get, but it can be true on a local scale. Many pollutants that affect human health and the environment are short-lived. They chemically react or decompose in the atmosphere over time instead of accumulating indefinitely. And for a lot of chemicals, there are concentration thresholds below which the consequences on human health are negligible. In those cases, dilution, or really dispersion, is a sound strategy to reduce their negative impacts. And so in some cases, that's what we do, particularly at major point sources like factories and power plants. One of the tricks to dispersion is that mini plumes are naturally buoyant. Naturally, I'm going to use a pizza oven to demonstrate this. Not all, but most pollutants we care about are a result of combustion, burning stuff up. So the plume is usually hot. We know hot air is less dense, so it naturally rises. And the hotter it is, the faster that happens. You can see when I start the fire, there's not much air movement. But as the fire gets hotter in the oven, the plume speeds up, ultimately rising higher into the air. That's the whole goal. Get the plume high above populated areas where the pollutants can be dispersed to a...
These are smokestacks. So generally speaking, since he didn't really reference, the ones that are really like thin and tall are the smokestacks, which are in a lot of those photos. But again, they had other things as well, just so folks are aware.
Minimally harmful concentration. It sounds like a simple solution. Just run our boilers and furnaces super hot to get enough buoyancy for the combustion products to disperse. The problem with that solution is that the whole reason we combust things is usually to recover the heat. So if you're sending a lot of that heat out of the system just because it makes the plume disperse better, you're losing thermodynamic efficiency. It's wasteful. That's where the stack comes in. Let me put mine on and show you what I mean. I took some readings with anemometers with the stack on and off. The airspeed with the stack on was around double with it off, about 1 meter per second compared with 2. But it's a little tougher to understand why. It's intuitive that as you move higher in a column of fluid, the pressure goes down, since there's less weight of the fluid above. The deeper you dive in a pool, the more pressure you feel. The higher you fly in a plane or climb a mountain, the lower the pressure. The slope of that line is proportional to a fluid's density. You don't feel much of a pressure difference climbing a set of stairs because air isn't very dense. If you travel the same distance in water, you'll definitely notice the difference. So let's look at 2 columns of fluid. One is the ambient air and the other is the air inside a stack. Since it's hotter, the air inside the stack is less dense. Both columns start at the same pressure at the bottom, but the higher you go, the more the pressure diverges. It's kind of like deep sea diving in reverse. In water, the deeper you go into the dense water, the greater the pressure you feel. In a stack, the higher you are in a column of hot air, the more buoyant you feel compared to the outside air. This is the genius of a smokestack. It creates this difference in pressure between the inside and outside that drives greater airflow for a given temperature. Here's the basic equation for a stack effect. I like to look at equations like this divided into what we can control and what we can't. We don't get to adjust the atmospheric pressure, the outside temperature, and this is just a constant. But you can see with a stack, an engineer now has 2 knobs to turn, the temperature of the gas inside and the height of the stack. I did my best to keep the temperature constant in my pizza oven and took some airspeed readings. First with no stack, then with the stock stack, then with a mega stack. By the way, this melted my anemometer, should have seen that coming. Thankfully, I got the measurements before it melted. My mega stack nearly doubled the airspeed again at around 3.5 meters per second versus the 2 with just the stack that came with the oven. There's something really satisfying about this stack effect to me. No moving parts or fancy machinery. Just put a longer pipe and you fundamentally change the physics of the whole situation. And it's a really important tool in the environmental engineer's toolbox to increase airflow upward, allowing contaminants to flow higher into the atmosphere where they can disperse. But this is not particularly revolutionary, unless you're talking about the Industrial Revolution. When you look at all the pictures of the factories in the 19th century, those stacks weren't there to improve air quality, if you can believe it. The increased airflow generated by a stack just created more efficient combustion for the boilers and furnaces. Any benefits to air quality in the cities were secondary. With the advent of diesel and electric motors, we could use forced drafts, reducing the need for a tall stack to increase airflow. That was kind of the decline of the forests of industrial chimneys that marked the landscape in the 19th century, but they're obviously not all gone, because that secondary benefit of air quality turned into the primary benefit as environmental rules about air pollution became stricter. Of course, there are some practical limits that aren't taken into account by that equation I showed. The plume cools down as it moves up the stack to the outside, so its density isn't constant all the way up. I let my fire die down a bit so it wouldn't melt the thermometer, learned my lesson, and then took readings inside the oven and at the top of the stack. You can see my pizza oven flue gas is around 210 degrees at the top of the mega stack, but it's roughly 250 inside the oven. After the success of the mega stack on my pizza oven, I tried the super mega stack, with not much improvement in airflow, about 4 meters per second. The warm air just got too cool by the time it reached the top, and I suspect that frictional drag and the longer pipe contributed to that as well. So really, depending on how insulating your stack is, our graph of height versus pressure actually ends up looking like this. And this can be its own engineering challenge. Maybe you've gotten backdrafts in your fireplace at home because the fire wasn't big or hot enough to create that large difference in pressure. You can see there are a lot of factors at play in designing these structures, but so far all we've done is get the air moving faster. But that's not the end goal. The purpose is to reduce the concentration of pollutants that we're exposed to. So engineers also have to consider what happens to the plume once it leaves the stack, and that's where things really get complicated. In the US, we have national ambient air quality standards that regulate 6 so-called criteria pollutants that are relatively widespread: carbon monoxide, lead, nitrogen dioxide, ozone, particulates, and sulfur dioxide. We have hard limits on all these compounds with the intention that they're met at all times, in all locations, under all conditions. Unfortunately, that's not always the case. You can go on EPA's website and look at the so-called non-attainment areas for the various pollutants. But we do strive to meet the standards through a list of measures that is too long to go into here, and that is not an easy thing to do. Not every source of pollution comes out of a big stationary smokestack where it's easy to measure and control. Cars, buses, planes, trucks, trains, and even rockets create lots of contaminants that vary by location, season, and time of day. And there are natural processes that contribute as well. Forests and soil microbes release volatile organic compounds that can lead to ozone formation. Volcanic eruptions and wildfires release carbon monoxide and sulfur dioxide. Even dust storms put particulates in the air that can travel across continents. And hopefully you're seeing the challenge of designing a smokestack. The primary controls like scrubbers and precipitators get most of the pollutants out, and hopefully all the ones that can't be dispersed, but what's left over and released has to avoid pushing concentrations above the standards. That design has to work within the very complicated and varying context of air chemistry and atmospheric conditions that a designer has no control over. Let me show you a demo. I have a little fog generator set up in my garage with a small fan simulating the wind. This isn't a great example because the airflow from the fan is pretty turbulent compared to natural winds. You occasionally get some fog at the surface, but you can see my plume mainly stays above the surface, dispersing as it moves with the wind. But watch what happens when I put a building downstream. The structure changes the airflow, creating a downwash effect and pulling my plume with it. Much more frequently, you see the fog at the ground level downstream. And this is just a tiny example of how complex the behavior of these plumes can be. Luckily, there's a whole field of engineering to characterize it. There are really just 2 major transport processes for air pollution. Advection describes how contaminants are carried along by the wind. Diffusion describes how those contaminants spread out through turbulence. Gravity also affects air pollution, but it doesn't have a significant effect except on heavier than air particulates. With some math and simplifications of those 2 processes, you could do a reasonable job predicting the concentration of any pollutant at any point in space as it moves and disperses through the air. Here's the basic equation for that, and if
It's interesting that he put the equations here, but this definitely doesn't seem like a simple version of explaining this to folks. I think he does usually show graphs and things like that, which I think are easier for most folks to understand. I don't know if this video in particular seems to be particularly like beginner friendly compared to some of the other videos I've seen by them.
Join me for the next 2 hours. We'll derive this and learn the meaning of each term. Actually, it might take longer than that, so let's just look at the graphic. You can see that as the plume gets carried along by the wind, it spreads out in what's basically a bell curve, or Gaussian distribution, in the planes perpendicular to the wind direction. But even that is a bit too simplified to make any good decisions with, especially when the consequences of getting it wrong are to public health. A big reason for that is atmospheric stability, and this can make things even more complicated. But I want to explain the basics because the effect on plumes of gas can be really dramatic. You probably know that air expands as it moves upward. There's less pressure as you go up because there's less air above you. And as any gas expands, it cools down. So there's this relationship between height and temperature we call the adiabatic lapse rate. It's about 10 degrees Celsius for every kilometer up, or 28 Fahrenheit for every mile up. But the actual atmosphere doesn't always follow this relationship. For example, rising air parcels can cool more slowly than the surrounding air. This makes them warmer and less dense, so they keep rising, promoting vertical motion in a positive feedback loop called atmospheric instability. You can even get a temperature inversion, where you have cooler air below warmer air, something that can happen in the early morning when the ground is cold. And as the environmental lapse rate varies from the adiabatic lapse rate, the plumes from stacks change. In stable conditions, you usually get a coning plume, similar to what our Gaussian distribution from before predicts. In unstable conditions, you get a lot of mixing, which leads to a looping plume. And things get really weird for temperature inversions because they basically act like lids for vertical movement. You can get a fanning plume that rises to a point but then only spreads horizontally. You can also get a trapping plume where the air gets stuck between two inversions. You can have a lofting plume where the air is above the inversion with stable conditions below and unstable conditions above. And worst of all, you can have a fumigating plume when there are unstable conditions below an inversion, trapping and mixing the plume toward the ground surface.
This visual was very helpful to follow this.
And if you pay attention to smokestacks, fires, and any other types of emissions, you can identify these different types of plumes pretty easily. Hopefully you're seeing how much goes into this. Engineers have to keep track of the advection and diffusion, wind speed and direction, atmospheric stability, the effects of terrain and buildings on all those factors, plus the pre-existing concentrations of all the criteria pollutants from other sources, which vary in time and place. All that to demonstrate that your new source of air pollution is not going to push the concentrations at any place, at any time, under any conditions, beyond what the standards allow. That's a tall order, even for someone who loves Gaussian distributions. And often the answer to that tall order is an even taller smokestack. But to make sure, we use software. The EPA has developed models that can take all these factors into account to simulate, essentially, what would happen if you put a new source of pollution into the world and at what height. So why are smokestacks so tall? I hope you'll agree with me that it turns out to be a pretty complicated question, and it's important, right? These stacks are expensive to build and maintain. Those costs trickle down to us through the costs of the products and services we buy. They have a generally negative visual impact on the landscape, and they have a lot of other engineering challenges too, like resonance in the wind. And on the other hand, we have public health, arguably one of the most critical design criteria that can exist for an engineer. It's really important to get this right. I think our air quality regulations do a lot to make sure we strike a good balance here. There are even rules limiting how much credit you can get for building a stack higher for greater dispersion to make sure that we're not using excessively tall stacks in lieu of more effective, but often more expensive, emission controls and strategies. In a perfect world, none of the materials or industrial processes that we rely on would generate concentrated plumes of hazardous gases. We don't live in that perfect world, but we are pretty fortunate that, at least in many places on Earth, air quality is something we don't have to think too much about. And to thank for it, we have a relatively small industry of environmental professionals who do think about it a whole lot. You know, for a lot of people, this is their whole career, what they ponder from 9 to 5 every day. Something most of us would rather keep out of mind. They face it head on, developing engineering theories, professional consensus, sensible regulations, modeling software.
This is one of the things that does make me feel better about this is there's so many engineers that are so good at so many things and specialized in so many areas that there's somebody who's thinking about every single aspect and detail of anything that could be going wrong in so many businesses and so many aspects, that there's an expert out there who spends all day every day thinking about these types of problems that you might not even realize exist.
Software and more, just so we can breathe easy.
Thank you for watching. I will see you around.